familiar with neurocomputation, some of this stuff is actually old. But recent developments which I've been working on, there's a connection to the older stuff. And so, but I don't think if you read a standard account of the older stuff, I don't think it's presented in a way that this connection is there. So that's what I tried to do with this talk. It's pretty experimental. Let's see how it goes. I'll do without a pointer.
The pointer will come.
Oh, okay. All right. So basically, so this is a picture of the brain, the only picture of the brain that we have in this talk. And the only reason why it's a human brain, the only reason why I put that was because before we go into details of concrete models, etc., I want to imprint on you that the brain is a very complex system. It's made up of different regions or areas, although, well, like, I don't know, this is the frontal part of the brain, right? This is just the part behind your eyes. It's called orbitofrontal cortex. Oh?
Sorry, we're trying to give you a remote control on that.
So we like to distinguish between cortical structures, which is well developed in human brains, and that's the major difference with other brains in nature. But there are also subcortical structures which are very important, like the basal ganglia, for example. So this at the back of the brain here is the visual cortex. The input coming from the retina goes through a part of the thalamus, which is called lateral genicular nucleus, and then they go to V1, the primary visual cortex, and then it goes through two pathways, one dorsal one, which is this one, and another ventral, which, according to current knowledge, or let's say popular theories, one deals with the positions where objects are, and the ventral one deals with the identity of objects, etc. etc. Now, there's a huge literature on this thing. So these are mainly results obtained empirically during, especially in the 50s and in the 60s, lesion studies, and then electrophysiology studies, etc. etc. I want just to point out that any real theory of the brain, or at least even a small part of it, has to take into account this huge, spectacular organization. And there's a lot of interplay between different brain areas. And more recently with functional imaging studies, for example, it can be seen more clearly than with other techniques that maybe it's not too false a statement to say that the whole brain participates in every single meaningful situation. Okay. But now we're going to forget all that, and we're trying to do. We're trying to study some more specific problems. But before we go into that, I want to show you that 150 years ago, it wasn't even clear that there were neurons in the brain. And so it wasn't until a Spanish neurophysiologist, a neuroanatomist actually, Cajal, improving a technique called the Golgi stain, was able to show unequivocally that you have these complex cells in the brain, neurons. This is the and so this is one of his original pictures, and shows a beautiful neural circuit. That's what we used to call, these days we call these things neural circuits, meaning that they are built in the way they're built to serve a function. Basically, that's what we think what we call the neural circuits. Okay, and so
are you going to give us some numbers, or how many neurons?
Well, there are more or less 10 to the 10 neurons in the brain, and 10 to the 13 synapses, which is the point of contact of neurons. I have no idea how they calculate those numbers. You find this the usual estimate. Yeah. Yes. Yeah. But I can understand how you do it for a piece of tissue, for the whole. I don't know. Maybe you do it. Maybe Laura knows. Maybe she knows. Do you know?
I think it's like you said, they take basically a block of tissue that's on average.
On average,
and extrapolate for one.
Yeah, I mean, the order of magnitude, it's presumably correct or not far off. And so this is this is pyramidal neuron, one of the major neurons in the brain. The soma is where the nucleus of the cell is, and it gets this. The input usually comes through this dendritic arborizations here. There are many of them that really packed very close together. And then you can record the neuron has a membrane which is polarized at best. So it's like RC circuit in its simplest modelization. And so this neuron, the membrane is always polarized at best, and can be more polarized if you inject an input or if it receives input from other inputs. And when this process is fast enough and strong enough to initiate an action potential, which is a waveform, an electric waveform that propagates without attenuating along an axis, which is basically this very long filament here that basically goes around and reaches another neurons, more or less the dendritic. I mean, anywhere really, even at the soma or anywhere, you get inputs from all over these parts here. And this is just a blow up, or for example, this would be two neurons which are connected together through this synaptic connection here. So an action potential traveling down this axis, and you get here at this point in time, at this point, through a very complex process, opens channels. These channels are permeable to ions. Ions go in and out the cell, and doing so they change the polarization of the membrane potential. And this is how basically the electrical signals are mediated by chemical activity.
Before you go on, we must use often this picture, but just to see if there's any details of it that are generally well. So you got many dendrites coming in, and one or two branches of the axon coming out in this picture. Now is that true always, that there's very few branches coming out?
Yes.
Okay.
But then at the end, the axon branches out.
So it
forms many synaptic.
It can go some distance and then it can branch out, or it
Yes.
can branch out along the way?
I think it's especially at the end of it.
Only at the end it branches, and then it could have some.
Yes, exactly.
And then is the dendrite to the soma, is that always much shorter, or can that be equally long?
It really depends on the neuron you're looking at.
Sure.
So into neurons, for example,
Yeah.
they have a much shorter axon because they tend to target neurons in their vicinity. That's why they call them the neurons, and usually they exert an inhibitory action of these neurons.
But is the dendrite ever long? I know the axon can be long.
Yeah, for example, if you in the cerebellum, there's a type of neuron called Purkinje.
So, yeah.
And that's a beautiful fractal-like structures in the arborizations. I don't have a picture here.
Those ones can be pretty long.
Yeah, but you find, in some books you find they refer to this as the zoo of neurons. But I would say, from our point of view, if we're going to be modeling networks, let's say, you will assume that the neuron receives hundreds of thousands of inputs and then targets an output neuron, a target neuron, sorry.
Well, once you got realized, it doesn't.
Yeah.
Well,
but what happens is it's much more complex than what we usually model. So, for example, we know now that once an action potential travels down the axon, it also gets back propagated out. So it goes, and this could lead to a nonlinear interaction between the input coming here and the output of the neuron itself that was induced by the inputs.
Is that known to something be important?
Yeah, for example, they're involved in several theories. For example, one is the gain modulation. The gain modulation is the property of changing. Well, it would be probably clearer in the next slide. But for example, they've been used in recent theories of learning. For example, so for example, synaptic plasticity. They would or could affect synaptic plasticity, which is the basis of learning, according to our belief. They could change the gain of the. So if you think of the input-output relationship of this neuron, the interaction with the nonlinear backpropagation could change that. Together with other things, for example, the level of background synaptic activity that could also impact the way. So this would be a modulatory influence on the output of the neuron given an input, whereas the input would drive the neuron. Okay. But there would be none of that, in the rest of the talk. So basically, that's what I took. When an input, when an actual potential arises in its target neuron, it will, transiently depolarize the background potential, and this typically through some sort of double exponential form, right? And it's the order of magnitude of 1 millivolt, what you see here. And when you get more inputs in in temporal vicinity, you can reach, let's say, so that you can reach threshold in a short enough time, you can elicit, the target neuron can in turn elicit action potential. All right. So there's some sort of temporal integration going on here. And for example, this interaction, this back-propagating action potential could change quite drastically this picture here, because instead of integrating, 20 or 50 inputs, only a few may be enough if you have this nonlinear interaction. So that adds to the complexity. But the neural computation based on connectionist models, you basically always see linear summation of the inputs, and then some nonlinear transfer function. All right. Okay, so a very important thing to know about what neurons do. So this is the train of action potentials emitted by a neuron in cortex. Okay. And then I think this is from cat visual cortex. I forgot to put the reference here. This is from Holt and others, 1997, I think. So if you take a piece of brain, so you cut, you literally slice, and then you patch a cell, meaning that you can inject an electrode into the cell, and you can stimulate with a current, a DC current like that. That's which of enough magnitude so that it can drive the neurons to fire action potentials. You would see something, some sort of periodic spike train like this. And one important thing that more recently has become mainstay of theoretical models is that in a real brain this never happens. Okay, so if you now take an intact brain, so this is from an anesthetized animal. So, his skull has been opened so that you can access the brain, but the brain is all intact. And so, whatever neuron you probe in now, this neuron is still embedded in this sea of synaptic inputs coming from other neurons. What you basically see, that's what in vivo means. You see that now if you inject the same kind of current, the spike train obtaining a response to it is rather noisy, or let's say irregular, right? It fluctuates in time. And now, if you actually use a visual stimulus, so even though the animal is anesthetized, you can basically open their eyes and flash stimulus there. Often they use gratings. People know what stimuli more effectively drive, given neuron, and so they try until they found one, and that's what you see again. So the idea, the take-home message from this slide is that basically, in the brain, spiking activity is irregular. It's often modeled as a stochastic Poisson process. So in the simplest case, it would be a renewal process, so like a simple Poisson process. One then tries to hope that with this you can capture enough of the statistical properties of this spike train. So for example, at this point you would, the simplest thing you could do is, okay, let's forget about, spike times, because maybe I should mention, if you do an experiment in vitro, so now on the slice, but you inject a variable input current, like Gaussian process, a stochastic process. This is the way you can actually recreate this activity in vitro. The response of the neuron will always be different. Turns out the more noise in your current, the more reliable the response is, meaning that you will always get this, the spike times. So for example, this will repeat itself quite reliably. If you inject something like that, though, or close to this, let me try to explain better. If you do this now, if you do exactly this experiment the second time, you will not get the same. You will get a periodic spike train, but the spike times will not align. All right. And this is just some intrinsic unreliability. No, the final rate is usually reliable, but the actual spike times is not. So-
aligned
You mean
with
the
what's
phase
on-
shift
I mean,
is
yeah,
shifted?
if you're doing something twice, then you do.
Yeah, that's a major difference between biology and
But what
physics.
defines the zero?
If you do something twice, you get two different results.
Yeah, but we're just trying to understand. You said-
How is it different? Is it
Sorry,
the
sorry.
phase shifted
What-
or
Yeah,
the
what
phase?
defines the zero at phase?
In this particular case, is you could, for example, you could
I mean,
you
from
could
the
not have
onset.
this doublet here, and then you could start. So that would just be for the third one on. It could
So
be
the
a shift,
so the delay from the offset, from the onset of the.
something like that. The firing rate. I mean, if you do this long enough, the firing rate will probably tend to converge. You know, if this recording is stable, there's not tampering with it. But another thing that you could have is, well, I'm sorry, I don't have
Well, the
pictures to
system
show
has-
you that.
Well,
But
the system has some state. I mean, I guess, you know, in broad terms, you postulate some state in the neuron, and if you postulate enough, you ought to be able to get it to reproduce if it starts out at the same state.
yeah, I mean, you can reproduce a lot. You can reproduce more or less the spike count in that temporal window. You can reproduce so many statistical features of it. But the exact reproduction of the spike times, it's not. You know, you can define a measure, a similarity between spike train, like a metric, okay? And so if they will not look very different according to this metric. I mean, sometimes you will, for example, you will miss an action potential, you know. Sometimes, for example, it also depends on whether this current is very close to the threshold or not. All right, so it depends on many factors, but the point is, if you have a current which is a bit noisy here, but not too noisy, then basically you get you know, stuff like that, and then this next time around this will be rather different. For example, you know, we would have 3 spikes here, only 1 there, and then 2 here, you know, and again and again. And if you do an experiment in vitro, you can try to control this because you have, you know, you have total control of the current and the situation, you know, and the conditions. You monitor the temperature, everything. You try the system. You hope the electron doesn't move. But for example, when you do experiments with behaving animals, so imagine a monkey is doing something and is seeing an input, a visual stimulus, whatever that is, and you find a neuron that actually responds to that stimulus, meaning that compared to rest, this neuron is now actually has a larger spiking activity. Even if you do the same, you know, same stimulus, same protocol, the monkey is fixating in the same spot, the spike train from this neuron will always be different.
I guess that wouldn't surprise us, as you started saying, it's very complicated.
Yeah, so yeah, some internal state of the animal may change, or this is an intrinsically noisy system anyway. The reason why it should be that way is not clear. So initially we thought, you know, like engineers would think that to make a system work, you want to increase this signal to noise ratio, right? And noise would be detrimental to your computation. But now we're getting more and more familiar with the idea that maybe noise is there for a reason. But this is a big something to do with the neural coding. And I will tell you in the rest of this, in the rest of the talk, we will consider one case where actually it is useful. In fact, it's necessary to have a noisy production spike trains. In other words, a situation where every time you have the same stimulus as an input, you want a slightly different spike train in the output.
But you're getting into, I mean, maybe it's worth just saying it more explicitly. I mean, given what you said, I mean, obviously there's some code, there's some rule that at least the rest of the brain uses to interpret what's coming out.
Yes.
You don't literally know that rule.
Exactly, yes. But, yeah. So, but you will see, in reinforcement learning is actually very important that you must have some source of variabilities out there. One locus could be the spike generation mechanism. It's not the only one. And in fact, you have it at all levels in the brain. You have it at the level of synapses. So synapses are unreliable. Sometimes when an input comes, they fail to communicate it. This is a very well-known fact, and there's a big literature about it. So, and you can exploit one or other of these noisy mechanisms to do reinforcement learning, which we'll go into. So anyway, so this is the knowledge you need to get to have to get to the how can I describe this? I would say this is the modern neuron, which is the best candidate for the kind of, for the modeling of network phenomena that we would like to. So it's simple enough that it's only it's a one differential equation. Right, so you remember potentially that every time you have this is an incoming excitatory spikes, and this will be incoming inhibitory spikes, for example. Every time an excitatory spike arrives, you have a little step up in the magnetic potential, and then it decays with some time constant. All right, and then if you have an inhibitory input, then this causes a downward deflection, and then the member potential continues to towards its rest. And when you have enough of them in a short enough temporal window, you reach a threshold, which in this very simple model is just a fixed number. In reality, it's not. You will say that an actual potential has been limited. And so you see, this is if you have the stochastic point processes as an input, you get a spike train in an output that is actually variable. Right? And then if you assume that your stimulus is, for example, coded by spike count, meaning that every time I see this, my input will be a new realization of this stochastic process, but the firing rate is the same, the spike count is the same. So the average, which defines completely a Poisson process, that doesn't change. So to each spike count, I can univocally associate a stimulus, then you would also have a different spike train in the output. And the problem, in this particular simple case, the problem with neural coding would be to do the solve the reverse problem. Given the spike out in the output, you want to infer what stimulus elicited it. And in this particular case, you assume that two different stimuli will have to elicit two spike trains with different spike count, with no regard for the spike times, for the latency, so how long before the first time came in, etc., etc. There's many different numbers of coding mechanisms that have been proposed. Temporal coding, firing rate coding, spike count coding, mean firing rate coding, latency coding, etc., etc., etc.
I just want to make sure, was the basic model he described clear to everybody? Because he gave a basic model of the neuron, he just didn't write it right. Yeah, okay.
So this would be the equation of an RC circuit. It's the derivative of the member potential equals minus the member potential plus the input. And the input is
contribute with this kind of time,
exactly,
time response function.
And this is difficult to study. When you have a point stochastic process like this. So, given that it's a fairly good approximation in the cortex to assume that you have a large number of tiny inputs that are required for the neurons to reach this threshold and meet an actual potential. Basically, you can do what is called the diffusion approximation to this model. So this would actually be, it's called the Ornstein-Uhlenbeck stochastic process, which is basically, it's a Brownian motion with a decay towards a steady state value. So it's what was invented to describe Brownian motion by Einstein in 1905 with decay. With boundary conditions, which are the emission of an actual potential, at which point the process gets reabsorbed from the source and starts again. And so you can do a lot is known about this process. The mean first passage time, which will give you the firing rate.
I'm not quite sure. So I understood the first model. That's with that's given a spike train coming in. That was deterministic. It was some specific time response function that we use in innovating. And now we're approximating or talking about a non-deterministic model, and it was to say that we superimpose, we have one, the state is a real number, and we kick it up or down depending on inputs, and it has a Brownian motion. Is that the model?
Yeah, so basically imagine that you having the
so driven by the
height of this input goes to 0, but the number of these inputs goes to infinity.
Okay, then that converges.
And then you converge to a step. So you have to be careful when you do the limiting procedure. You have to use the rules of Ito stochastic calculus to do this. Not in the simplest example, it's actually very easy. But the general theory is basically a way to regularize the results that were obtained.
So we model each pulse in B as
right. So you would. What I didn't show here, basically, the input is not shown here. What would the input look like? Pretty much like this. This would follow the input with a little bit of lag because it has an exponential decay. So it's again, it's a low-pass filter of the input. But the input is basically, you go from a stochastic point process like this to a continuous process, which is like random motion or almost. And this is just an integration of that process with this boundary condition when it spikes. It's just a continuous version of this model here, and it's easy to treat mathematically.
But at what point did the stochastic, did you assume the stochastic?
These are both stochastic because the spike train is a stochastic process as well. So
well,
given
but if we give a particular drive, spike train.
if this is fixed, the response is always the same. It's not.
And B is deterministic in that sense, and the input might have some stochastic. Now C, you're saying the same, or C?
No, this is the same here. If the input is not stochastic, this also will not be
It's not
stochastic.
stochastic, it's just the input. Okay.
Do you have an equation describing all of this, or you're not going to show it? Or
No, it's not important.
Huh?
It's not important.
It's not important.
Find the equation easier than the equation.
Yeah. I can. You want to see the equation?
Yes.
I'll show you the equation.
If you have.
Yeah. Shall I write it over there?
Why don't you run that?
Okay. It's just I want you to have a notion of what an integer fine unit is. That's all I want you to know. But so the model on the top will be a simple, so you have a capacitance of the membrane, and this is the membrane potential. All right, and this is your rest value divided by. Let me get the thing right. Here probably resistance. All right, and your time constant of decay to B rest will be given by the resistance times the capacitance. So low pass with RC circuit decay, right? Plus your current. I think the range is not right. Now, what is this current? This current in the model on the top will be sum over spike times K, T minus Tk, all right? And then I would say, let's assume all the excitatory inputs are the same, so I call them J, E. That this is the amplitude of my excitatory input. And you would have the same, in that particular case, you also have an inhibitory spike train, so you would have plus Ji, sum over, let's say, J, delta spike train here. And this is negative, okay, so this will be this gives a negative contribution. And this is a stochastic point process. All right. So if you write this here, this will be the equation of the integral fine neuron driven by a Poisson point process of a given firing rate. So if you take the temporal average of this, if you integrate this and then divide by the temporal window, this will give you the firing rate or the spike count of let's say FE, etc., etc. Now, from this you can do midfield theories, etc., 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 and you can do population density approach. But this is, I'm not going to talk about this at all today, so I don't want to go into it. Now, the diffusion approximation to this equation, I cannot write it this way because actually the function is not differentiable. Right? Random motion is not differentiable. It's continuous and is nowhere differentiable. So that's why you have to come up with a new calculus, which is called the stochastic calculus. And there are two versions, one called the Ito calculus and one the Satonovich calculus. And they give the same results if the noise is additive, like in this case. If they multiplicative, meaning that you multiply this by B, then they give this result C. If this process is not correlated. But now, I mean, this is really kind of technical stuff that is kind of
you just give the idea.
not useful. So the equation for the only process would be divided by tau times dt plus, and then you have the current. Okay, this current you write it this way. It's a Gaussian process. Okay, plus that, and then plus sigma, and then have sigma. All right. So you see, this should give you a hint why this is not differentiable. If you divide by dt,
But mu are the same kind of inputs you were putting before.
yeah, so basically, this now will be your input I, and this written like this doesn't mean anything. It only makes sense when you put it in an equation like that. And if you take the diffusion approximation of this equation, you end up with something like that. And this is when you simulate. Okay, what is this? This is white noise. So it's a stochastic process which is zero mean, and it's and the covariance is delta function. That's why white noise. If you look at this autocorrelation function, it's just a delta. All right, and more realistic models of neurons have some autocorrelation in there. All right. And this is due to the fact that input from synapses are not actually delta functions, but are more like things like that, as I showed you before. All right, so if you replace this by this, you do the same limit, you will get something which is an autocorrelation function. But it doesn't matter. So this is white noise. So every single time, every dt, you throw a dice, you get. So you get a number, it's going to be positive or negative with the magnitude of the same probability. And you can solve this process exactly. So you can, for example, you can find out what's the probability of having, it's a stochastic process, right? So it's not a deterministic process. To define it completely, you need to define the probability distribution. It's pretty easy to find out the average and the variance in this process without knowing the probability distribution with a few tricks. But the whole probability distribution is known. It's a Gaussian distribution. So the probability of V at time t is a Gaussian distribution. This follows a Gaussian distribution with mean I hope I remember these things correctly. And then the variance is going to be, I think the variance of this process is sigma squared tau divided by 2, 1 minus sigma 2, divided by tau, so the time constant. Alright, so I've used this notation here, Gaussian of mean m and variance s squared. So this is the variance, this is the mean. These are the station, so when time, after a long time, this process will converge to a stationary distribution of mean, mu, and variance sigma squared tau divided by 2. And so if you were to simulate this, let's say you start from 0, right? So you have a transient which goes with this time constant, you get something like that.
And then you're still going to use this so that when you get to some threshold, you've got.
This is the free process, so-called.
Yeah.
All right. So this will be the stationary process after the transient. The transient is about tau. Right. After this transient, you converge to starting from 0 times 0. You converge to a Gaussian process. So the probability distribution is Gaussian with mean mu and sigma squared tau divided by 2 being right in this. And now, how do you make it into a model of a spiking neuron? Basically, you say now there is a threshold for spike emission. So this is 0, your resting potential, let's say. So without an input, you will be around. You will be, without an input, you go to rest, right?
Is there a lower bound?
Sorry?
Do you put in a lower bound by hand, or not? Like you put on
In this particular case, you don't need it because it will go to.
Well,
it will turn to this.
But so it can go arbitrarily low. Like so
If you drive it, yes. If you drive with lots of inhibition, yes.
Oh, okay.
But in an absence of an input, it will stay around rest.
On average.
Yes.
But not.
Whereas Brownian motion, for example, the variance will diverge. And so in that case, you will model neurons that based on white noise, they need a lower bound for depolarization. So what you do, you start from here, then you convert to the stable state. Let's say this is your input current. Let's say this is the current you injected into the neuron in an experiment. Okay? And then occasionally, you see here, occasionally you have an action potential just because of fluctuations. Let's say that we had another one here. And so this is your boundary condition. If at time t star, you have the d t star is threshold, then you have a spike. And the process is reabsorbed by any point. Usually, conveniently could be this one, for example. Here I clearly reabsorbed it from here, let's say, or very close to the threshold. But more conventionally, you just reset it to a value, then it starts again, and then you reset to a value, then it starts again. Now, if you have an input current which is very strong, so you're in a sub-threshold regime, which is called, but basically this neuron is going to fire all the time. Irregularly, because you still have some fluctuations, but at one point all of the fluctuations will completely disappear. And we think that in cortex, the regime of neurons is, the regimes in which causal neurons work is they have an input coming from other neurons, which is usually sub-threshold. But with fluctuations around the steady-state value, which are enough to have them. And you can make this neuron fire a spike train, as irregular as you want, by working on these parameters, sigma, tau, etc., etc. And sigma and mu can be actually directly linked to biological things like the amplitude of the EPSP, the time constant of the receptors that may give the current, etc., etc., etc.
Well, why mu has to be a constant? I mean, if you have the input from the other neurons,
in theory,
you can have time dependent values.
Yes.
Right?
Well, yeah. I mean, you can have. This is just. Let's assume you have only one type of input with a given time constant.
So here is a constant.
No, wait. This is the time constant of the, with which the member potential goes back to rest once you remove the stimulus.
No, I mean mu.
Mu is the average of the input.
Yes, yes. But in principle, it's coming from other neurons.
Yes, it's coming from other neurons.
So you can have a time variant.
Yes,
So,
of course. No, this works exactly the same if you have, if mu depends on t and sigma depends on t, and in fact can even depend on v. The theory of this process here, it's exactly the
but
same.
then the solution wouldn't be like this.
The solution.
Yeah, because here is time independent. I mean, if it's a function of v, then the whole diffusion equation is not going to be a Uhlenbeck process. If it's dependent.
Yeah. You're right. I mean, you wouldn't have this. You would have the integral of yes, exactly. But you can formally integrate. So this bit here you can formally integrate it as if this was a deterministic system. So you would have the integral of this function that, if it's constant, you end up with the exponential. And for this one is similar, but the integral is a stochastic integral. But okay, so you don't have exactly this. It's true. You have an inhomogeneous process, meaning that it's mean changes over time, and the variance can change over time. But you can calculate, you can integrate it, and you can simulate it and stuff like that. So this would be a noisy-driven integral-defined neuron in the diffusion approximation.
So why did you pick this stochastic process one? I mean, there are many, of course, choices. Is this the simplest in a sense?
The simplest is Brown motion, but it's
no, but
this is the. Well, it's also. I mean, this has been. This description of the membrane of neurons is very good. So this builds directly on this one. But I can tell you, there are a big number of modern neurons, especially in the past 5 or 6 years. One is the adjunct neuron, particularly when alpha equals 2. It's a very important model because it's been shown in many applications actually. But when I mean important, I mean it's simple enough to be studied, but also captures the essential features of the phenomenon we want to study. So, for example, if you study hippocampal oscillations or hippocampal precession, the quadratic integral neurons, it's very good to do that. There have been experiments trying to find out which model describes the real neurons best, and that depends on what the real neurons are. And the animal is, the area, cortical. And the way you do this is very smart because you can, for example, you can do some sort of Fourier analysis of with particular inputs, have many systems, and you can find out how quickly the response to a particular input lags, etc., etc. And then you can find out what kind of exponent you need there to get a better match. And the beautiful thing is that what we found was that the actual neuron was able to follow very fast input fluctuations much better than the model. But the best description was with an exponent between 1 and 2, close to 2. So I guess if you wanted to study that particular system, you could use this, the quadratic neuron. Anyway, this is a big field itself. Does that satisfy? Because
Maybe we should head back out of here.
I can't get beyond my introduction. It's a curse. How long are we gonna? We're gonna get hungry when we work on it.
Yeah, we go till like 1 o'clock. So it's not reasonable people. It's just 12:20 now.
All right. So all I wanted you to take from this is that this is a model of spiking neuron, which is actually quite good. I mean, it's good enough for most purposes. Now, one thing that we always look at, electrophysiologists very often look at, you take a spike train like this, and you just look at the spike count, number of spike divided by the window. All right. So, and then you can build this firing rate curve. Given the intensity of the input, assume that this has been induced by an input current like a DC current. All right. It's not the case here because of this convexity. Because this convexity here, that means that actually the input was noisy. And this is called the response function, transfer function, and it's the crucial ingredient to do meaningful theories of populations of plug-in neurons. And this is the response function of that neuron that now we have the equation, the Einstein with the boundary condition. So you can actually solve this analytically. I didn't write down the equation, but it can be approximated to very good within 5% or something by the hyperbolic tangent or something. It's some sort of sigmoid. Okay.
What's S?
S is it's what they call a sigma there. Only different units. These are actually picoamps. This is nanoamps, so this is the correct units for current. So 0, it means this is not noisy driven. So it would be the model at the bottom, right? With the DC current. So the current is just a steady current, and you see there's a logarithmic divergence of the derivative at the threshold. So before this point, the neuron doesn't do anything, but as soon as you go above the threshold, you have already a finite spike rate. Now, this is regularized if you have some input, some noise in the input. Okay. And these curves is what you do. If you draw a straight line here, you will see that there can be two stable fixed points, and this is the starting point for doing midfield theories of stability in the current networks, which is something I worked on in the past, but this is not about it. It's not about this. What neurocomputation has been doing for a long time is just to go. I mean, sure that you have. If you think of perceptions, for example, your unit, your neuron, is either a spin, so something has only two values, 1 or -1 or 1 and 0, or some sort of it's defined by some sigmoidal activation function, something similar to this, but more symmetrical, like hyperbolic tangent, or the logistic if you want to go between 0 and 1 instead of -1 and 1. And in the limit so the deflection of the logistic function, the sigmoidal function, will be related to, when you do the statistical mechanics of spin neurons, will be related to the inverse of the temperature. And in the limit of having no noise, basically you end up, it's like the hyperbolic tangent converging to the sine function, or whatever translated if you go from 0. And so, when you have a two-state neuron, which is usually a lot of work on statistical mechanics and neural networks, uses this kind of models, that's the idea, this is where it comes from. So you have a spike trains, which is actually very regular, and then you make a current, a response function, and then, so you get something like this, and then you go to the, you just consider two states of the neuron, quiescent or active. Now, it's a very crude approximation, but then the point of this theory is actually to study the collective aggregate behavior of these systems, right? So this is, I mean, this goes a way to go from the biology to, you know, what we actually retain of all of this, and using our models to do that. And these actually, these are real response function curves of real neurons. These are pyramidal neurons. No, these are interneurons. So these are inhibitory neurons of rats of the sensory cortex from a region that is called layer 2, 3, and layer 5.
And what are the different curves?
And these are different values of the noise. So when you probe the neuron with this stochastic process, which is mu and sigma right there, if you increase sigma, you will go.
So you're putting in a signal and you're putting in more or less noisy signal.
Exactly. So this is exactly the experiment that corresponds to what I showed you there.
So the black thing is a DC signal and then the other is...
No, there's not.
The bottom curve, what is that?
This is almost a DC, yes. Almost a DC signal. Almost a DC. Because if you inject a DC, the neurons don't like it very much.
Okay.
And since to get a steady-state response function you have to record for a long time, you get into trouble. But the idea is that, yes, this should be
very little noise.
very, very little noise. So it's, for practical purposes, this will be the response to the DC. Okay, and so, and these are the data points. And the curve, this is the best fit of this neuron there. And this is the theoretical one. You can fit the parameters. Neurons all has 5 parameters that you can tune. And you tune them for each data set for all points. So you need, I mean, if you only have one curve, you can fit anything to it. Parabolic tangent, you fit. I don't know, something like that. Yeah, exactly. Because if you let it go that way, you wouldn't be able to. But if you have more than one curve, then it becomes tricky. And the point of this study was, can actually real neurons be reproduced, correctly or to some extension sufficiently described by an interdefined neural response function? And the answer was yes. Even though the neurons is a very complex thing, it's got this dendrite, back propagation, all these things I told you about before. So this is actually...
The noise is white noise?
The noise is, again, you cannot do white noise because it's an idealization, so it had only 1 millisecond correlation there. So basically, instead of having a train on delta functions, you have an exponential that basically goes back to 0 very, very quickly in 1 millisecond. Now, the resolution was 0.2 milliseconds here. So it's, but yes, because this theory, I mean, that theory works if you have white noise as an input. Otherwise, much more complicated. There's not, I don't think there.
Are you saying the noise is correlated with the 1 millisecond? I forgot which.
Yeah, that would be correlated to 1 millisecond. And we've also done, okay, so we've also done with 5 milliseconds or 10 milliseconds. The curves don't look very different. But we don't have the theoretical response function to fit to them.
But
I guess you could simulate it and change the parameters, simulate the change the parameters. They're kind of similar if you have 5 or 10 milliseconds correlation left in the.
So then you add the memory to the noise.
Yeah, exactly.
This is non-Markovian. I mean, the whole process is non-Markovian.
No, this is Markovian.
No, but when you add the correlation, like.
Yeah, that's right.
Yeah.
I mean, the neuron's response is not Markovian.
Yeah.
Well, I mean, the theory is, I mean, the results that we white noise driven because we have a theory for that, and we don't have any memory, so we couldn't do this. All right. So this is the first part of the talk. Before was just introduction. but we can, I mean, we can continue another time. This is just a kick-off of our weekly discussion.
Yeah, we'll continue.
Right, so we can just do
get
this.
So,
Right.
only have like half an hour.
So, I mean, this talk was supposed to be about learning, okay? So, the neurocomputation approach to learning, this is a very famous example, is the perception. Okay? So, this is just a simple network when you have, each input is defined by a string of n values. These values can be, for example, 1 or minus 1. So you have 2 to the n possible strings that you can give as an input. They're connected through these weights, which are adjustable, to an output unit y. And this basically sum up the inputs and kind of integrates it. So, for example, a parabolic tangent would be, that means that the input is integrated like that, or a sine function would be that you only have. And this is exactly what I showed you before. So this is a very crude approximation of what actually a real neuron does. And the task of the perceptron is given a number of labeled patterns, input patterns, you want to associate them with a label. So basically, for each input I give you, there's a number p of pairs, right? Each pair is made of the input and the output you want to respond. For example, for input number 1, you want plus, let's assume you're doing the sine function, you want plus 1. Input number 2, you want minus 1. And this problem is the same as trying to classify the inputs in 2 classes. Those that get into the plus 1 class and the minus 1 class, there will be 2 classes. Okay. And it's basically one way to solve this problem, given that the solution is this, is to use, method of supervised learning, where you use the information, you know what the desired output is, and you change the weights so that you get exactly the desired output for each input. Now, the perceptron learning rule was invented based on heuristic, heuristic reasoning. Okay, because it made sense, and then it was shown that theorem was shown that basically tells you that this learning rule works. But I'm going to derive this learning rule from a more principled approach, which is a gradient descent in a narrow function. So let's start from the simple case of linear units. So now your output unit is not does not take on only values plus 1 or minus 1, but basically the sum of the weighted inputs, kind of the whole range. All right. So in other words, the phi function is the identity function. All right. So consider the average of the error you make when you present the input randomly to the network. One after the other, chosen randomly, many times over and over again. You can define the average error that you make. So this is the output for input ni, and this is the desired output. All right. So this is only different at 0 if you make an error, if you misclassify it. You want to minimize this. So what you do, basically, you take the one way to do this is to move in the direction of the gradient, and the derivative of the energy function here is very simple, and so you end up with, in fact, the perception learning rule, which is also called the delta rule, which is this rule here. Now, look, it makes sense because when you present pattern number ni, let's assume that you got you classified it correctly. So this difference is 0. You don't do anything.
What's eta?
Eta is a learning rate, so it's a very small parameter, and there are conditions on eta for this to converge to the solution. So for stochastic gradient descent, the typical condition is that this depends on the time step, and the sum of eta from t that goes from 1 to infinity should diverge, but the sum of the eta square should converge. So for example, if eta is 1 divided by t, where t is the time step, that's okay.
What?
So this learning rate tends to be smaller when you converge to the solution.
I don't understand your error function. Why is there this factor of p? to the
Sorry,
u?
sorry, I forgot to say. P ni is the probability of presenting pattern ni.
Oh, it's not a power.
No, sorry. Yeah, all these things up here, these are not powers, only the 2 is a power. So, yeah, and every pattern has to be presented enough times. So this probability has to be non-zero for all of them.
I see. So most common patterns are weighted 1. That's all it means.
Yeah, but to do things, anyway, the best way to do this is to present, on average, all patterns the same number of times.
So then there's no p.
Well, then the P would, yeah, P could be constant. I mean, it's just a fancy way to write this. Yeah, I could have just written sum over the patterns of the square difference and present the patterns deterministically. 1, 2, 3, 4, ni, 1, 2, 3, sorry, P, etc., etc., etc. But this is just, I want you to get used to this because in reinforcement learning, you use a stochastic procedure to do things, and so usually you always have probabilities of random presentation, etc., etc. So suppose now that you misclassify. So for example, you wanted to classify these patterns as +1, but you didn't. So your response was -1. Okay, so this is going to be positive, which means you're going to increase the weight, which is the right direction, right? You want to increase the weight because next time around you want to have +1 as an output, not -1. And vice versa, if the misclassification was in the other direction. So, okay, so these were linear units, remember. The original perceptual rule was devised for threshold units, so now the perception only has an output. Okay, so sorry. Before, it wasn't just +1 or -1, because this is, right, this could have different values, right? But it doesn't matter, it's the same. Now, it can only be -1 or +1, you will see the learning rule is exactly the same, reads exactly the same, then it is different because the values are different. But so you do exactly the same thing here. You would like to do exactly the same thing, right? So try to use some gradient rule. But the point is that since the output is just a sine function, the gradient of this energy function where it exists is 0. Okay, so you can't use it. So let's see how we can make this happen. So this is just to say this, the same. It's just what I showed you before. Written slightly different. This is a multiplication of. It's an inner product of 2 vectors: the weight vectors and the input pattern vector. All right. And so the output can only be +or -1. If you develop the square here, you get that each square value has to be 1. Right. So this would be P and P, you sum them up, it's 2P, so it's just a constant. And then you have the product of the side output and the actual output you get as a function of the input and as a function of the weights. So you can write this energy function as a constant minus this quantity here, which I call the total reward. And so minimizing the error is the same as maximizing this reward. Why do I call it reward? Well, because a reward is a feedback signal that tells you if you did right or wrong. So in this particular case, if you classified correctly, the reward should be 1. If you misclassified it, it should be -1. And in this case, you see, you only classify correctly if the side output and the actual output are the same sign. So this is always 1 for a good classification, always -1 for misclassification. And so the problem can be cast in these terms. We want to maximize the reward. And now we have, in a very, very subtly, gone from supervised learning to reinforcement learning, which in this case is pretty trivial because when you only have 2 possible answers, the 2 things are the same. But these can be generalized to real reinforcement learning situations. Okay, and they have some sort of have the same mathematical structure somehow, and so that's why I'm presenting things in this order, in hopes that we can at one point appreciate this correspondence. So,
how does that? I'm being stupid. I don't see that identity.
Which identity?
Why can you pull the y into the sign down below there?
Oh, because y can only be plus 1 minus 1.
Right.
But so.
Oh, okay, yeah, of course.
Yeah, it's just-
It's an overall sign.
Yes. Okay, so the idea. So as I told you, this gradient here is over 0, so you can't really do anything. The idea is to replace the sine function with a different function, which is this one. Okay, this is the definition of the function, but it's actually easy if you just look at the graph. Okay? So now your function to be maximized, instead of being the sum of the sines of this, would be the sum of the g of these arguments. And the thing is that the global maximum of the original reward function is actually also global maximum of this function. So we'll try to maximize this function. Now, if you look at the gradient of this function now, okay, as long as errors are made, it is different than 0. So the gradient is 0 here, but you don't care, you don't want to do anything when you have a good classification. Right? And in this case, you actually want to change things. And if you do the gradient of this function now, you get that. And this, so this would be the part where reward is -1, mixed classification, and this is the part where reward is +1, good classification. So and only when you misclassify, you apply exactly the same rule as before. So you end up exactly with the same rule, right? Okay, and this is so for threshold units. So these kind of units, as I told you, this was proposed based on intuition and based on the fact that it resembles some sort of Hebb association rule, which at the time was the big idea in the field, etc., etc. And people have been able to show that given p linearly separable patterns, and this p has to be less than 2n, this learning rule will actually converge to a correct classification of all patterns in the finite number of steps. Right? So the fact that you doing stochastic gradient descent here does not tell you this kind of information. Right? That doesn't tell you how long it will take to converge, if it converges at all, and what kind of subset of patterns it will converge. Okay, but this is just to touch base, which is very important. So, next comes reinforceable learning. Okay, now we're talking about stochastic units. So before we had a deterministic unit. The output of this unit was the integral of the input. It could be +1 or -1. It could be a hyperbolic tangent of the input. But given the input, the output is actually deterministic. Now, using more or less the same equation, but given a different interpretation, okay, imagine that units are stochastically activated. So you have an input current or a field, and this field is always the same thing, would be the sum field would be this. The sum of the inner product. Let's call this U, this would be the field, and depending on the magnitude of this field, you have a given probability of having +1 or -1 as well. Okay, this would be a stochastic unit. If you have a stochastic unit, that means you have a probability of a given output, y. Let's say y is +1 minus 1, given the input. Your goal is to maximize the average reward, right? Exactly the way we did it before. And with the same method we used before, with gradient descent, in the average reward. So this would be the learning rule, right? All we have to do is to calculate the gradient of the average reward. Okay. So this is the basis of, basically everything has been done with this after Ron Williams in 1992 published these results, which is based on a very simple insight. So it took the average of the reward. This is the sum of the input-output pairs of the reward given the input and the output. The probability that depends on the weight of having a given output given the input times the probability of the input. Alright, this is just the average. If you take the gradient of the reward, the only thing that depends on the weights is the probability, the conditional probability of having the output given the input. Right? But something like that, I can't really sample it because I'm missing the probability here of having x and y. So what I do, I divide and multiply by this probability. And now the derivative of this probability divided by the probability is just the derivative of the log of the probability. Okay? And now, though, I have again the joint probability of x and y here. So basically, this is an average again. And so this can be written as the average of reward times the derivative of the likelihood of having the output y given an input x. And this is valid for arbitrary networks. It's a very general procedure. So the likelihood is sometimes called, it's indicated with letter L. This is not really, this is just to simplify the notation. Basically, this L here means the derivative of the likelihood of having output y when the spike train shouldn't appear here yet. But since it's there, I'll tell you, this is the great thing about this. You can actually apply this to neurons that emit spike trains, not just plasma spin neurons or firing rate neurons. Okay? The derivation will be exactly the same. Now, in case of spike trains though, y is a spike train. So something extended in time, characterized by a sequence of times, for example. Or it could be, even if you want to consider the temporal potential as well, it would be the whole process. And x is the input. So a spatial temporal part of the spike trains. We'll get to that. So this generalizes the spiking neuron. And I'll give you an example with spin neurons just to see how this works. So just take a logistic function, right? So instead of this being the activation function of this output unit, now this is the probability that the output neuron is active. So kind of same equation, different interpretation. All right? And the probability that it is not active is 1 minus this one, so this is the logistic function. So we know that the derivative of the logistic function can be written as a function of the function itself. And then for the learning rule, remember you need the derivative of the likelihood, which from there it's easily, it's very easily obtained. We already have the derivative here, you just have to divide by the function itself, so you get this if the output was 1, and this if the output was 0, and you can write the whole thing with a single expression, which is this one. Because if y is 1, then you have 1 minus f, this is 0, you just have minus f. Beta controls the amount of noise in the system. Let's say this would be the beta is the inverse of the temperature, so it tells you how steep this model function is, this logistic function is. And this will be your learning rule. So you change the weights. So your new weight is your old weight plus a learning rate, eta, times the reward, times the likelihood of the probability, which we calculated, and it's the output of the spin neuron minus the probability that the output is 1 times the input. So this is very similar. Well, it's not very similar, but you had this term, the input, it's the same as in the delta rule for the perceptron. But then, of course, this is different. You have a reward here, which modulates the learning rule. So I've done this for just one output neuron, but if you have more of them, so your output is not just one spin neuron, but is a number of them, by using the property that these outputs are conditionally independent given the input, you basically, the learning rule factorizes. So for each weight, you can just do it independently. Now, if you were a biologist, you will notice here that you have 3 terms in this learning rule. One is rewarding, so this is the information whether you got reward or not. And in the brain, this information is actually broadcast to synapses through neuromodulators like dopamine. So we know that happens. There's a lot of literature in how dopamine affects synaptic plasticity, for example, in the cortical striatal connections, which is a system that is very important for reinforcement learning. It's a system that connects the basic ganglia, the cortical structure, to many other cortical structures, like prefrontal cortex and many other places. This is a postsynaptic term. What do I mean by that? This has to do with the output of the neuron. You see, this is the output, this is the actual output, this is the probability of being activated. So it's similar to the instantaneous firing rate, you know. It's wrong to say it that way. But, so when the probability, all you do here is you compare what the neuron actually did to what its probability of being activated was. Right? And this would be positive if the neuron was active, even though the probability was not very large. It would be negative the other way around. And this term is presynaptic, because that basically is the contribution, and in biological terms this would correspond to the EPSP coming from the dendrite of this neuron. So you have reward, post, and pre. This is a 3-term learning rule, and there's a big community that trying to find out exactly what this rule look like in when they study synaptic plasticity in actual brain tissue. So they have to patch 2 cells, verify that they are synaptically connected. Then they apply protocols of induction. They would apply an input. They could force an output. So for example, they can induce an actual potential with a second electrode, and then they can change the concentration of dopamine, and then they look what kind of learning rule they obtain. And as a theoreticians, what we can do, I mean, this point of view is that you derive the learning rule from the first principle of maximizing encourage reward, and then you try to check this model against the data. That's one way of doing things.
Is there any consensus about whether that works? Whether you can...
Oh. If you read a review about synaptic plasticity, you have to be prepared to find, I mean, it's a bit unfair, maybe I shouldn't say that, but almost for each rule you will find the opposite. So it's a big, you know, it's...
Well, maybe if you talk about slight variations between rules, the general picture looks okay. We could be saying that two pieces of evidence point in the opposite direction. So.
No. I mean, so there are many theoretical learning rules and also experimentally verified synaptic plasticity rules.
Okay.
And
some broad terms.
and you find some degree of agreement between.
Yes, a broad terms the answer is yes.
So for example, at the beginning, the learning rules that we had, right, they only depended on, for example, relative firing rate, pre and post synaptic firing rate, like Hebden. The simplest implementation of a Hebden rule would be that. That doesn't consider what the level of the member potential is, right? And then there was a very famous celebrated learning rule, this BCM learning rule, where they actually okay, I think that learning rule was actually introduced to solve a problem that in Hebden learning you have that for linear neuron, for example, it doesn't converge. The more potentiation you get, the higher your weights, blah, 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 blah. And BCM came out with a learning rule that does as some sort of internal threshold for which would bring the value which is movable. It's a dynamic threshold which will restore the values of the weights back, you know, to prevent these runaways, synaptic weights, etc., etc., etc. More recently, there have been learning rules, for example, proposed by Stefan Fusi, Daniel Amit, that look at the member potential, not only at the spike times. One of the most famous rules that have been discovered in experiments is the spike time independent learning rule, which only look at the difference, the relative timing between pre and post synaptic spikes. And you find that if the presynaptic spike precedes the postsynaptic spike, in a short temporal window, you get upward potentiation of the synapse, and vice versa. So you get something like that, okay? But then again, after the first study, many studies followed, and depending on the preparation, depending on the animal, depending on the age of the animal, basically you get a number of these things, you know, sort of being symmetrical, would have one long tail on one side, or would have almost no LTD component. So there's a lot. I mean, yes.
About the details, but the biggest difference between this and these older ideas seems to be the R and this modular.
This is actually, I would say, it's more recent. So the older ideas, like the perceptual learning rule, you don't have this. You just have pre and post synaptic. So in head rule, you would look at the pre and post synaptic activity. So experience dependent activity. So
people agree that the R really is there, or in real systems.
Yes, we know that it is there. But I mean, when you do head learning, basically you're doing unsupervised learning.
Right.
So you're looking at what the learning rule does in that case. It kind of abstract regularities in the inputs.
So that opens a lot of questions. Again, pretty much all the neurocognition and textbooks we look at don't have that R, or at least if they do, they don't really do anything with the R.
That's true.
And now we could ask a lot of questions about how, if we believe the R comes from dopamine as a modulator, how that actually works in the brain, or just even time scales and distance scales and so forth.
So the reason why in the textbooks, basically, there's a huge literature in supervised learning, like, for example, perceptual learning, backpropagation, support vector machine, all these, tools, or unsupervised learning, like heavy learning, or attractor neural networks, so networks that tend to have a stable attractor, like Hopfield networks, which it's a bit weird there because in theory they're unsupervised, but in practice you give a prescription for the synaptic matrix. So you put your solution already in there. So some people consider that actually the Hopfield network to be a supervised model. It's a bit of a grey area there. But the standard interpretation is that they're unsupervised learning. So you have a huge literature on unsupervised and supervised learning, and very little on reinforcement learning. But this, I would say, in the neurocomputation, artificial intelligence, in machine learning, literature is not true, because reinforcement learning actually is a field of machine learning that experimental psychologists have kind of resonated with to try to explain association like Pavlovian conditioning or instrumental conditioning. But basically, you need to learn to do a task by interacting with your environment, and the only feedback you get is whether you did it right or wrong. This is a very important, crucial form of learning, and every time we do an animal experiment in the lab, that's how they actually learn the task. They have to try, okay, what do you want me to do? Oh, I need to touch this, and then you get reward. If I touch the incorrect one, they don't get reward, and they have no idea. They only know that they were wrong, but they don't know what the right answer would have been, right? So in the parlance of perceptrons, the input are not labeled. You don't. Well, no, they are, because we know, but they don't know what the correct response is. And it's a huge field, so I'm particularly interested in reinforcement learning, because I think it's a more, kind of a more fundamental type of learning, really. But it's also, compared to supervised learning, is much more limited, of course. But it uses very, very limited feedback. So should we stop, or?
Because we're almost at 1 o'clock.
Yeah, so basically, let me tell you where I am now. So the idea now is to see how this can be used with spiking neurons. So with neurons, with modern neurons like that. So now you will have time into these equations. Here there's no time. I mean, there's just time step if you want. But the spike trains, a neuron now does something like this. And so I would say, well, if I have at least one spike in response to temporally extended stimulus, I classify as +1. If I have no spikes, I classify as -1, and actually this is what is called the tempotron. Would be the analogous of perceptron in case of spike neurons, and I believe Raymond Son's coming here, right? So he's recently had a paper with Sampoliski on that. And so this would be the same kind of classification task you do with perceptrons, but now the input and the output has extended spatiotemporal patterns of signals, and these signals are basically the spike trains, these neurons. And so you can actually do, the point is to do something similar where, X is a spike train, the pattern of spike trains, Y is a whole, output of this neuron, and you have to calculate the log likelihood of having a particular spike output given the input. And now you have to define what your code is. Because, so you have to say, let's say that I only care about the spike count. If I have more than 20 spikes, it's +1. I classify. Less than 20, it's -1, right? So what I need to calculate, given my modern neuron, for example, that one, is what's the probability, given the input, that I get more than 20 spikes or less than 20 spikes. If I can calculate that, I can apply this kind of thing. And this is basically where I'm going now. And then the last part of the talk would be how to use that to do something more advanced, which is now the inputs are clearly defined. So you present an input, you want an answer. And now imagine a situation where you don't know what the input is, you have a continuous stream, like in speech recognition, right? And there are relevant segments. If you do the right thing in response to these segments, you get rewarded, otherwise you don't. And you don't know what the segments are, you don't know the boundaries, so you have to segment the input stream. And I want, you know, the question is, can I do this in a population of spiking neurons using a reinforcement learning group of this type, gradient learning type. And there's a very nice theorem that has been proved in 2009 about this. And I don't intend to go through the proof of the theory, but I can give you the reference if you want. You can read it.
Okay, I mean, this will be interesting to hear. Now, as Giancarlo mentioned, in 3 weeks from today, we will have a talk, I think at this time period, if it's good, by Remy Monisson, who is, you know, again, from this general school of physicists who took up computational neuroscience and all everything. And we'll probably ask him to speak about, again, this general area. He's worked on a variety of things. Now, would you like to speak again before that, in like 2 weeks, or would you?
Well, now the talk is pretty much prepared, so it's really up to you.
Right. What do people think? I mean, I'm away next week. That's why I'd like to wait 2 weeks. Should we do that?
So same time, same place in 2 weeks?
Yeah.
That's part.
Okay.
In time, some place in 2 weeks.
Yeah.
So I'll check my agenda.